This way, okay, good afternoon, everyone. Welcome back to the afternoon session. And so we'll start with the hands-on session on integrated demographics. I'm Ilaria Pascucci, professor at the University of Arizona, as a month ago at Galen. Now Dr. Bergsten. And you will learn how to debias Exoplanet surveys to calculate intrinsic occurrence rate, not only from one survey, from multiple surveys, and also to integrate them, which is really a novel thing. While using these tools, I want to encourage you also to think about the science you want to do. All these tools are built to learn something about the physics, so try to think how you can connect the demographics to your science interests and to physical processes that are relevant to understand what is seen. So that said, I want to invite actually everybody who is on the back to come closer, right? Because there is space and you can hear better. So take a few minutes to come closer, and then Galen, please take it away. I'm here if you need help as well.
All right. Hello, my name is Galen. You can scoot up if you so choose, feel free. I'll also preface that if you are a person without an orange lanyard, i.e. just a regular workshop attendee, you might also want to position yourself next to people with orange lanyards who are our hands-on session helpers for the day. So while I will be able to answer hopefully most questions that people have, they can also try to help you out with any like Python related things or clarification questions. Okay. Sweet. So a brief introduction I gave you yesterday talking about what we're going to do today. But as another refresher, we're going to talk about exoplanet occurrence rates. You've heard this term come up a bunch in the talks so far, but it's the idea of trying to estimate how common planets actually are from our very, very biased survey data. And to do that, we're going to run through a series of exercises in a Google Colab notebook. So just as a refresher, if you head on over to the workshop website and you haven't been there already, there's a page on the hands-on sessions. And if you click on that, there's a bunch of instructions, including a full PDF on how to set stuff up. For our purposes, if you have already done that, then I would invite you to scroll down to like the bottom half of the second page where there's some details on the first hands-on session. In particular, we're going to be using this second of the two notebooks. But before that, if you haven't run the setup notebook for this session, also be sure to click on that. And you'll be able to run through some processes of like downloading the code and data and notebooks and things and getting that set up onto your Google Drive. And then once you do that, I invite you to click on the second of those two links, which will bring you to an actual notebook for all the stuff that we're going to do today. So I'll give you a couple seconds to maybe run through those if you haven't already. And then I'm going to do the same. I'll also, as a brief precursor, it might be useful for some of the stuff that we're going to do today to change the runtime type. If you are using Google Colab, there's a tab at the top called Runtime. And if you were to click on that and then go to change runtime type, you'll be able to specify which hardware you're actually running this notebook on the Google Cloud servers. And after a bit of testing between me and Elise and Melanie, it seems like things tend to run better on GPU processing. So if you set this to T4 GPU, then it might work just a little bit faster, hopefully. Okay. With that, before we dive into the code, I want to give a couple intros and thanks to some very wonderful people. First of all, thanks to all of you for being here. I appreciate you taking the time to tune in, learn about occurrence rates, and I'm happy to help out. I also am known to chronically talk fast. So if at any point I am talking too fast and you get lost in the sauce, you can just hold up like a little fist or some hand sign to ask me to slow down, and I will endeavor to do so. I also, again, want to shout out all the folks in orange lanyards, our hands-on session helpers who attended some training sessions to learn what the heck is going on and also be able to help you out with different questions. And then extra special shout outs to the folks that helped organize this whole thing, especially Melanie, Elise, Tracy, and Chaz. Truly the MVPs of this whole affair and the only reason that any of this got together. So thank you very much. Sweet. Let's get into it. As a brief overview of the stuff you can expect to learn today, we'll talk about how to actually calculate occurrence rates, which are, again, this sort of debiased metric of how common planets are. And these make up sort of the backbone of exoplanet demographics. This is how we understand our survey data and connect what we observe to planetary populations so that we can learn things about planetary physics. The main exercise today is going to be focusing on giant planets, and we'll talk about some of the interesting physics there and what we can learn by doing demographics with them. But the whole point of this workshop and the software package called Bardic that you'll get to play around with is that it can do any kind of planets that you might be interested in. So maybe you don't work on giant planets and you work on small planets, or maybe you work on like a really specific type of giant planet. No matter what you do, we hope that these can give you some tools that you can apply to your own science. And I'm going to try to wrap things up a little bit ahead of schedule today so that if folks are interested, you can come chat about some ways that you could apply this to your own work and stuff that you do. I've split this up into roughly 3 chunks of the Colab notebook. We'll start with a very slow introduction to like what the heck this code is and how to use it and how to access different data, and go through some rudimentary like occurrence rate calculations for some like simple use cases. And then we'll spend the second chunk talking about occurrence rate modeling for giant planets with one survey. And then we'll end by talking about occurrence rate modeling with multiple surveys and a couple different types of models and the nuances therein. So if we hop on over to our Colab notebooks, and you run through the first couple cells that are all just like setting things up, giving Colab access to the files that it needs in your Google Drive, importing some of the relevant Python packages like MC, and then after that, there's a little preamble about what this code is. I've had a couple questions already. So to clarify, this code isn't out yet because I defended and then went on vacation and time got away from me. So you get a little teaser version. And eventually, when we finish things up, a fuller version of this code will be available online with a bunch of documentation that is hopefully legible. But instead, for this workshop, you have a sort of micro version of the code where we've streamlined some stuff. We've given you pretty much only the data that we need to do things today and simplified some of the calculations so that they run faster on like educational timescales. But if there's anything here that you're interested in and you want to know, what does the full version include, then at any point, feel free to interrupt me and we can talk about that as well. So once you have imported the Bardic packages, there's a couple different classes and functions and things that we'll use. We'll also make use of some very standard like NumPy, PyPlot type stuff. So if you have experience with plotting in Python, then great, I'm happy to help. But if you don't, then also some of our hands-on helpers will hopefully be able to clarify that with some of their own expertise. In Bardic, or in this sort of survey ecosystem, hold on, I've gotten eager looks. Okie dokie. So as a show of hands, how many folks have gotten through that sort of preamble? Things are running okay. Like half-ish? Okay. Feel free to keep working through stuff. And if you do have any issues, hit up the helpers, hit me up, and I'll give you a brief introduction to what this code is before we get into actually doing things. So Bartik is a software package that's split up into a series of classes to handle different parts of occurrence rate modeling. There's a class that handles survey data. So for any exoplanet survey, it uses the same infrastructure, the same code and nomenclature to like access and store and process the data. And that all happens through the survey class. So we'll start by looking at an example from the California Legacy Survey as a radial velocity data set, but literally everything we're about to do can be applied to any of the 3 surveys that are in this version of Bartik that you have, which are California Legacy Survey, again, radial velocity, the Kepler survey, which you've heard a lot about, especially in Josh's talk this morning, coming from the transit method, and then some direct imaging data coming from the SHINE sample of exoplanets. So, I want to see if the hands have gone up. Who has made it through the sort of preamble, setup, importing process now? Okay, a higher hit rate. So I will take that as a good sign. Sweet. So let's start by just running this first cell, which all it's going to do is load up the files, and there won't be anything to see on your end. But once that is loaded, they are stored as objects in Python, which are just whatever you name it. So in this case, I've called it the CLS object. So you can call that whenever you want to do stuff. But there are particular attributes for ways to access different information as a part of that survey object. This table gives you a brief description of, I think, some of the most salient or important parts of that. Probably the 3 most important are the first 3. So there's a table of stars, which includes all of the stars that were observed as part of this survey, and has different properties for those stars that are relevant to the stuff that we're going to do today, things like mass and temperature and radius. And then there's a table of planets that has a bunch of relevant properties for the planets, like their size, their separation, some other stuff that we might talk about. And both of those tables are formatted as pandas data frames. So if you've ever worked with those, great. You might be an expert already. If you haven't, we'll go through some examples of like how to use pandas data frames and play around with some of that data. There's some other things in this table that we probably don't have to focus on too hard today, because a lot of these things happen sort of behind the scenes when you're doing the calculations or like trying to estimate occurrence rates. This is what we call metadata. Jesse, I think, will give a talk on metadata on maybe Friday, but it's all the kind of stuff that you need to calculate occurrence rates, but also is gross and messy and gets swept under the rug because it involves a lot of math. So usually sane people will ignore those and insane people will make it their job. So the one other thing that I do want to point out is the completeness. We talked a little bit about this. You heard about like how do we actually measure survey sensitivity, and how do we access this information. So that's typically stored as this dot completeness attribute, which I'll show you a visual example of, but it is quite literally a grid that tells you how good you are at finding different types of planets. So to access some of this information, you can run this cls.planets code that just calls the planets attribute, and it'll print out the pandas data frame table. So to briefly explain what some of these columns are, the first 2 are just identifiers. That's what the ID stands for, S for stars and P for planets, respectively. So those are just the names and numbers that we've given to distinguish all these objects. And then the rest of these columns are all different physical properties of the planets that we've measured. So there's periods and then some uncertainties on the periods for the orbital periods of the planets. There's metrics of their mass. Radial velocity as a method measures approximately the minimum mass of planets. So there's that information. And then there's some extra information like what is the semi-major axis? What is the installation or the flux of these planets at their separations? That sort of thing. Again, we won't worry too much about the raw data, but I wanted to give you a brief introduction to some of these columns, just in case, whenever you want to make plots or you're working on your group projects and you want to check out different planets or different properties, this is kind of how you would access that by virtue of these pandas data frames. All right. I'm going to keep checking how we're doing. Who has made it this far? Is anyone? Okay, great. Seems like the same number of people, so that's good. Is anyone like particularly lost or like having trouble running stuff? Please feel free to raise your hands. This is interactive. We are here to help you. Okie dokie. I'll also mention that at any point you should be free to interrupt me and ask me questions. This is supposed to be an interactive session, so we are here to interact with you. Okay, so some more information on these planet tables. I mentioned that they are our pandas data frames, so we can mess around with those in a couple different ways, not the least of which is query language. If you've never used the query function before, this is a really typical way to like filter tables and access specific parts of information. So in this example, we are simply filtering along the mass column of this table to select planets that have masses between 1 and 30 Earth masses. Most of these columns are in units of like Earth days, or like Earth days, that's another thing. Like Earth masses, Earth radii, days, that sort of thing. And most of it should be documented, but I can clarify whenever needed. So to do that, you can quite literally just build a simple query string that says, I want masses between 1 and 30 Earth masses, and that'll filter for you a smaller version of the table. So this is just a little subsample of that bigger table that has a whole bunch of planets from this survey, but just the teeny ones. If you want to query these for whatever group projects or plots that you want to work on, there's some other examples of like how to structure queries, because it's sometimes weird seeing it for the first time. But you can also build queries using variables or like formatted strings. So this is just another example of that, where we've specified different ways to store that information and then fit it into a query. Fairly straightforward. Okay. Next, I have a visual example of how to access the survey's completeness data. So this is, again, using the same, oh yeah, question. Yes. That's a great question. All of this data is pre-downloaded in this little software package that you have. So it's in a static format that is not necessarily coming from the archive. Most of the stuff that you'll use today are from individual survey data sets that come from largely publications. And I think we posted those publications and original sources on the hands-on session page. But like Kepler, for example, the table of Kepler data is coming from the final data release 25 of Kepler, which is stored on the archive, but it's static. It doesn't get updated like other archive planets do, or like individual planets. When we get better observations, it's just as it was, uniformly vetted from the Kepler pipeline. And that's the same process for all of the other surveys as well. Okie dokie. So this cell is really just a lot of like plotting and pie-plot notation, but the part that I'd really like you to focus on is this set of lines here. What's most important is this part cls.completeness, which is specifically calling the completeness grid, which is formatted two-dimensionally to tell you what the completeness is as a function of planet separation and size. And then the other aspects, X grid and Y grid, correspondingly tell you the physical units of what those dimensions are. A lot of times in this presentation and throughout this session, you'll hear X and Y referring to the planet separation and size, respectively, because this is sort of the format for how we do things in demographics. I'm going to zoom out. Okay. Teeny. But as a brief example, let me shrink this. Perfect. So here's a very typical look at a completeness plot, which you'll see a bunch of today. The color map is showing, in this case, the California Legacy Survey's sensitivity as a function of both semi-major axis, so in terms of AU, and then the minimum planet mass makes up the sort of Y dimension or the vertical axis here. I briefly introduced the idea of survey sensitivity, but to run through it again, the stuff where it's bright and yellow is where we are really good at finding things. And then the stuff where it's darker and purple is where we are pretty bad at finding things. So you'll note that this particular sample falls in sort of the middle regime where we are okay at finding things. We for educational purposes, we made sort of a cut at 0.1 AU, so we won't be using some of those today, and I can explain why if anyone's like really interested, but the short reason is that it's gross and the math is hard. So we're mostly going to be focusing on this sample of planets. You'll note that there are some in regimes where completeness is like moderately okay, which could suggest that because you are sensitive to them, it makes sense that you would find them if they were there. And then in this bottom part where sensitivity is pretty poor, the fact that you find them suggests that there might be a lot of them, because even if you're really bad at finding them, you still manage to find some, which would mean that they are very common. Go ahead. It is an artifact. It's not real. So as part of my it's bad and the math is hard explanation, pretty much the left side of this plot is where things get funky coming from radial velocity statistics. So we've sort of truncated this just so you don't have to worry about the artifacts. So pretend that it isn't there and it's behind a curtain, please. Tracy. Oh, yes, sorry. The question in particular was like, what's going on with this little corner? Why is it bad? Okay, so a brief overview of how to access some of this information. Temperature check. How are we feeling? Are we lost? Do we understand what's going on? I got, okay, like 3 thumbs up, which is maybe 1% of the room. Okay, thank you, thank you. Okay, well, yeah, we'll pick things up from here. So I'm going to jump over to PowerPoint and give you a little bit more context about what we're going to do next. This is a mess. So let me introduce it to you line by line. We're going to briefly talk about this thing called the inverse detection efficiency method. This is the simplest way to calculate planet occurrence rates. And it is fast. It's very efficient, but it also has some shortcomings that we'll get into. The idea is that if you have a sample of planets and you have metrics for your survey sensitivity to those planets, you can estimate their occurrence rates in a couple quick steps. The first is to pick some range of planets that you are going to be looking at. In most cases, we do that by defining a box in terms of planet size and separation, which is this little purple rectangle that I've drawn here. And then once you've done that, you can count up the contributions from each of your planets. So in like math notation, you would do sum over the number of planets that you have. But instead of just like adding the number of planets together, for every planet that you have, you'll weight it inversely by 1 over the sensitivity to those planets. So completeness, sensitivity, roughly interchangeable. But basically, for every point that you have in your planet sample, you ask, what is the sensitivity to finding that exact kind of planet? And then you do 1 over that to basically counteract the bias that you have towards finding that. And then the last step is to divide that total sum by the number of stars that you have to compute a relative occurrence rate for number of planets per star. It is a fairly straightforward approach that really only needs these 2 things, and it works very, very fast. But there's an obvious limitation in that it only works where you have planets. So you can't estimate occurrence rates with this methodology if you don't have planets, because there's nothing to count up. And you similarly can't use it in regimes where you haven't constrained your survey completeness, which is less common, but sometimes still a problem. So as a straightforward-ish exercise, what people will usually do is define like a range of bins to calculate their occurrence rates over. So rather than just looking at like one box to say something generic about all planets within a particular regime, you'll usually slice that up into several little boxes. In this case, I've drawn some boxes as a function of semi-major axis. And then for those planets, you can calculate in those bins what the occurrence rate is. So the planet sample on the left is the Kepler sample of giant planets in a very particular regime of size and separation. And the color map in the background is Kepler's survey completeness, which for large planets is roughly constant as a function of size. And then using those metrics of completeness and the planets that you found, you could estimate what the frequency of those planets is as a function of semi-major axis to show you this increasing trend that I think I introduced yesterday. So let's do this on our own using Google Colab. So in this next section, we're going to switch to working with Kepler data just to match the stuff that I just showed you. So once again, we'll use the exact same notation to build up that survey object that includes the Kepler survey data, and it'll pull everything we need from that static data release 25, including all of the Kepler completeness metrics. And then I'll introduce you to probably the most important thing that is in this code. And you'll see this again and again. It's a dictionary object called criteria. And this defines all the stuff that we're going to focus on for our occurrence rate calculations. So I mentioned like drawing a particular box of sizes and separations. This is where we do that. So first, you'll have to define what planet properties or dimensions you actually want to do this calculation over, and you'll understand why that's useful later. But for Kepler's case, the things that it natively measures as the transit method are planet orbital period and radii, so you could specify those. And then draw some boxes for stuff that you want to look at. In this case, I've said periods between 1 and 40 days, and radii between 1 and 4 Earth radii to focus on like a subsample of close-in small planets, for example. And then there's some other things that will mostly remain unchanged for the rest of this workshop. There's this thing called use weights. There are sometimes, for certain surveys, extra statistical weights that we can put in to further mitigate biases that aren't captured by our survey sensitivity. Josh hinted at this, that there are, for the Kepler sample or for transits in general, there's like a metric called reliability that helps us filter out like astrophysical false positives and statistical false alarms. So we can put that all in one like quantitative number and then further weight those contributions through the inverse detection efficiency method. That was a lot. It's a lot of jargon. What's important is that we are doing things better when this is set to true. So don't change it unless you want to, and then you can see what happens. The other two things are at the bottom of this, which is further filtering this data set to a very particular set of host stars. You heard a little bit about how demographics change with stellar properties. Like we got a taste of like different metallicities, for example, in the transit talk this morning. And masses with the RV talk. But the idea is that you could filter your subsamples of planets to focus on particular types of stars based on particular properties of those stars. For this session, we're just going to focus on sun-like stars in general, which I have roughly defined as FGK stars between like 0.5 and 1.6 solar masses. But as one of the group projects, for example, you could have the option to explore how occurrence rates change with different stellar properties. So you may come back to this. In any case, you're going to be seeing this criteria dictionary and all of those things I just ran through a whole bunch. So I want to pause, see if anyone has questions about like what those different things are, what they do. Yeah, go ahead. Fair point. Yeah. What does the keyword use stellar do? This, because I'm bad at coding when I wrote this, it just tells the code to look for stellar criteria. I actually don't know what would happen if you turned use stellar off, but then still gave it stellar criteria, but I'm guessing it wouldn't work. So usually those two things are done in tandem, but thanks for the suggestion. I'll put it on my list of things to code better when I have time. So once you have that criteria dictionary set up, actually calculating the occurrence rates is pretty straightforward. So I showed you those different steps that are involved. And for convenience, those are all wrapped up into one function. So under the functions package, there is this function called IDEM, which stands for Inverse Detection Efficiency Method. And the only two things that it needs are the survey object that is storing all of your data and the criteria object that is storing all the things that you want to filter for your data. So if you have those two things together and you run this cell, it'll do two things. First, it'll print out the number of planets and the number of stars involved. In this case, we have like 2,000 planets that fit that bill, around like 115,000 stars, which if I was good at math would probably be like 1% or less. But if you implement the bias corrections, the second number that comes out is the bias corrected occurrence rate, which is like 40%. I have a PhD, so I can tell you that 40 is greater than 1. But hopefully that conveys the sort of scale of how important these bias corrections are to adjusting for, our observed frequencies and converting them into intrinsic frequencies. For the most part, we're going to tuck that IDEM function under the hood and use some other functions that do fancier stuff so that we can not have to call it like a bajillion times. But I wanted to introduce it to you just so you know what it's doing. And that function gets used a lot for a bunch of different routines that I'll introduce to you now. We can also remake that plot that I just talked about. This is, again, focusing on this like small close-in sample of planets. But in this next cell, it has one of the plotting functions from the plotting subsection of this package. The notation is to plot your survey occurrence one-dimensionally. I'll get into a two-dimensional case in a second. But by one dimension, I mean plotting the occurrence as a function of like just one planet property. So in this case, plotting the occurrence as a function of orbital period. Someone, I think it was Brandon, asked me about like number of bins, which you'll also see is a thing that you could specify here. This is largely visual. There's like not great rules for how you choose the number of bins. There's like a statistical theorem, and I think it's boring. So mostly today we're going to go off vibes and try to pick a number of bins that feels reasonable. In this case, a somewhat standard default is to just specify 10 bins, but feel free to mess around with this. So by bins, I mean how many individual points get plotted here. So like how many slices of the sample it's divided into, but you can also change that. Question? Yes. What are these bins? Perfect. As I'm a visual person, so here's like the visual I tried to come up with. By number of bins, this is sort of what I mean. So like if you were to draw these bins down and like separate your sample into little slices of semi-major axis. And so the corresponding visual is like each of these points have some range and they are evenly log spaced. So the bin edge is like exactly between each 2 points. But those are like the columns of orbital period that you are calculating your occurrence rates in, or the columns in semi-major axis. Does that help? Yes. So just as a like quick visual, if you wanted to do like 5 bins, for example, you could do that. And it would basically squish those things together into half the number of bins. When you're working on like your group projects or stuff like this, you can vibe with it, play around, feel free to see what looks nice, but also feel free to set the bins comically high or comically low to see how, you know, your choices of dividing the subsample are affecting the visuals and the distributions that you see. This next example is using pretty much the same notation, but the one difference is rather than plotting survey occurrence one dimension, it's plotting it two-dimensionally. So the inverse detection efficiency method is binning things as functions of both their separation and size. In the above plot, we had sort of marginalized or like combined over all of the sizes, but you don't have to do that. You could split it up even further into some arbitrary number of bins. So in this example, in the same way, we're specifying some number of bins for both the x-axis and the y-axis. And then the color map here is roughly the occurrence rate. So this is just showing using the inverse detection efficiency method with this relatively small sample of planets. What does that occurrence rate look like sort of two-dimensionally? And I won't get into like why it, actually I will. Is anyone interested in why it looks like this? I can soapbox for a little bit. Okay, yes, head nods. So in the same way that with the one-dimensional distribution, we see this sort of increasing trend as you move farther out. So going to larger orbital periods, you can see pretty much the same thing in this plot, that for all rows, the colors generally get lighter, which means that the occurrence is getting higher as you move farther out. So that agrees with the sort of marginalized trend here. This is somewhat common planetary physics, that as you move farther out, going from like super close in, like 1 day or less, to like 10 days or so, there's sort of an increasing number of planets, and then it maybe starts to plateau or like flatten out at the very least. And then in the same way, generally, we think that the occurrence distribution of small planets favors smaller planets. So if you were to look at the now going down the columns, it generally, the larger planets like Neptune sized up at 4 Earth radii, these tend to be a little bit less common than their smaller, like Earth sized counterparts, at least for Kepler. So that's a little interpretation of this plot. In either case, that's like a hyper-fast overview of the inverse detection efficiency method. If you are super, yeah, go ahead. Yes. What is the trade-off of increasing bins? So, and to make a brief comment about uncertainties, generally, the uncertainties on these points through the inverse detection efficiency method scale with the number of planets that you have in that bin. So when you have more planets in the bin, your uncertainties will be smaller. It's sort of typical Poissonian error bars. Conversely, when you have less things in your bin, your uncertainties will be larger because it scales with 1 over the square root of your sample size. So as an example, if I were to super increase the number of bins by like a factor of 5, um, wow, that looks abysmal. Sans the numbers that are in the way, you'll note that there are a lot of holes here. Those are like the white spaces are places where there is no information. There's no planets in that particular bin because we've made the bins arbitrarily small. So a lot of these bins probably have like 1, maybe 2 planets in them. So usually you don't want to go that small. Instead, I am always in favor of like picking some number that is less than 10 so that you always have at least a few planets. There's like, again, not a hard rule for how to do this, but favorably, if you can, like with a sample as big as Kepler, having like 10 planets or more in a bin is ideal. You usually don't want to go smaller than that. But we'll also see an example of with the direct imaging data set we have, there's 6 planets total. So there's not a lot of ways that you can bin that and have reasonable uncertainties. So we'll have another example of this later on, but hopefully that clarifies your question. Sick. Okay, we've already finished the first part of this by introducing to you these different survey objects and the different ways to calculate and plot occurrence rates with the inverse detection efficiency method. I want to pause before we talk about other things, see if there are questions, how people are doing. Yeah. Yeah, Ilaria raised a point about Yes. Ilaria raised a point about bin sizes and how modeling differs from the inverse detection efficiency method. So to give you a little teaser, the conversation we just had about like, does bin size matter and what does it do to your uncertainties is largely restricted to the inverse detection efficiency method, which by definition has to use bins. We're going to soon introduce to you a different way to calculate occurrence rates, which doesn't use bins and is completely agnostic to how you divide your subsample, so it doesn't matter. And that's generally preferred because it is less sensitive to some of these arbitrary calculations. But modeling is also like hard. So it's always good to have both. Other questions? All right. Is anyone, again, be honest, feel free. Is anyone lost? Can we help you? How can we help you? How are we doing? Okie dokie. Yeah, Stuart. Oh, yeah. Good clarification question. Stuart asks, like, when doing this setup, where does the stuff go? It goes, if you're using Colab, it'll go onto your Google Drive. So I actually have my example pulled up, but it's in some series of subdirectories that I believe starts with SSW 2025 for some Sagan Summer Workshop, and then goes farther down based on what session you're doing. So we're in hands-on session 1 doing exoplanet occurrence rates. But here you'll actually, I think, intrinsically, you'll sort of see this folder called Bardic_Sagan, which has all the stuff that we've been talking about so far. Yes. Okay. To clarify Lara's question and concern. In the Colab notation so far, you may have noticed some of these like orange circles and blue circles as emojis. The orange circles are like Google Colab user type stuff. And the blue circles are if you're doing this like locally, like you're running this code on your own machine. I should have checked if anyone was doing that. But as like a caution, if you are running on Colab, don't run the blue stuff because it'll have a bad time because it tries to do things on your own machine, but it's not on your own machine, if that makes sense. Other thoughts, questions, concerns? Sarah. Yeah, okay. We have touched on the IDEM function, but were there other aspects to the question? Could you? The short answer is nowhere. Most, if not all, of the documentation for this stuff exists in this specific notebook. But if you want to learn more or you have like specific questions, A, hit me up. But B, you could always go into your Google Drive or the directory that holds all of this information. And then the folder specifically labeled Bardic has the actual .py files for all of these things. And if you were to go into the functions, which is where that IDEM function is defined, you can check out like what it is actually doing under the hood. There's some inline comments and hashtags. I apologize that it's not the most thorough, but if that doesn't help you or you don't want to do that, because I get it, then please feel free to chime in and ask any specific questions or clarifications that you have. Sick. Sorry, could you clarify? Okay, yeah. Okay, yeah. If you are peeking at the .py files, like where does it come from? How did the like descriptions get added? That's all me. So you can blame me if it looks bad, but if it looks good, I did it myself, and that would make me very happy. Yeah, so this is all Galen made. And if there's any like particular things, like if you are poking, you have clarifications, let me know and I'll make it better. Okay, thank you. Sweet. Okay, so if we are feeling good so far, we're going to kick things up a notch and talk about occurrence rate modeling. I gave you a very brief introduction to this yesterday, but now we're going to talk about like what it is, how does it work, why is it useful? So as a brief preamble, on this plot, I've added to that occurrence rate distribution of giant planets from the inverse detection efficiency method, the stuff that's in blue. There's now also a gray line, a black line with a gray envelope that says model. And this is the type of stuff that this code is really built to do. So it's sort of the main function and where it shines. But also, a lot of times I get asked, did you just fit a line to some points? And the answer is no, it's a lot harder than that. So I wanted to give you a sort of brief philosophical understanding of like what the heck is going on here and why do we do it the hard way. In general, when we talk about occurrence rate models, we're talking about like a planetary population model. So rather than just fitting a power law, we're actually fitting a description of the entire planetary population, typically as functions of a bunch of different planet properties. So keeping up with this notation, often occurrence rate models will at least be defined as functions of planet separation and size, or X and Y in most cases. And so sometimes I hate showing you equations, but it may be conceptual to think about like what occurrence rate models are actually doing is trying to constrain the occurrence rate as a function of different properties. So in this case, we're going to fit an occurrence model as a function of separation and size. So the notation would be like the occurrence rate over whatever properties you're using. Then there are two things that are sort of critical to have to describe that kind of model and like parameterize your description of the planet population. The first is an overall occurrence rate. The sort of standard notation for this is F_0. You'll see this a lot, both in the code and in a lot of like occurrence modeling papers. This describes like the total occurrence rate. You could also think of it as like a normalization factor. Like if you are fitting a power law, how high should that power law go? So if you like integrate your model over the entire range of planets, you would recover exactly this number, which tells you the average number of planets per star. Then the next thing is what's called a shape function, which is literally the shape of your model, which describes how the occurrence rate should change or be distributed as functions of different planet properties. So in typical notation, it's given this shape function g, which takes at least planet properties like the separation and size, and then also free parameters that describe what is going on in the model, because we're going to fit models, so we can make it so that we actually constrain what those free parameters are and like optimize what the best fit distribution of these planets could be. In this example of a power law, the shape function is extremely straightforward because it is just a power law. So you just have the planet separation as a function of some power law slope. So quite literally, there are two free parameters actually. There's one for the overall occurrence rate and then another for the slope of this thing. I introduce it because now we're going to see some code that actually has a lot of those variables often written out, and will make a literal Python function to describe the shape function. So if we hop back over to Colab, there is a modeling section that describes this modeling class and how you can define and fit and access occurrence rate models in this code. Once again, it is using the exact same criteria dictionary because we're going to filter and select our planets in the exact same way. So none of that notation is changed. This is, I think, the same table that appears above just for your convenience. In this case, for this quick exercise, we're going to be looking at giant planets to match what I just showed you. So for Kepler, we could roughly define that as anything from like 6 to 14 Earth radii, which is perhaps generous, but good enough. And then now, in this case, I've made one slight variation. I've said that we're going to look at things as a function of semi-major axis instead of orbital period, just because. And then also looking at things as a function of planet radii, we'll specify the ranges that we want to focus on and fit our models over. And then the other two lines are exactly the same, focusing on sun-like stars. So if you run that, then you can load up now the Kepler survey data in pretty much the exact same way. But there is one curveball, one slight change. So this next cell is loading in Kepler data using the survey object, just as we've seen before. But there's an additional line that talks about, it's called .remap. Transit surveys or transit data generally measure things in terms of orbital period and planet radius. So for this exercise, to look at things as a function of semi-major axis instead of orbital period, you have to do some magic to translate those inherent measurements from period to semi-major axis space. It's just Kepler's third law, but rather than making you code out Kepler's third law, there's a function for it. So all this is really doing is taking Kepler's survey completeness and translating it from the period radius plane to the semi-major axis radius plane. And once that's done, that's all of the pre-formatting for the data that you have to do. And you only really have to do it for Kepler because a lot of other surveys report their stuff in terms of semi-major axis. So I just wanted to introduce that because you'll see it a lot when you specifically use Kepler data. Anyways, once you're good to go with importing your survey, as we've done before, and now you can make a modeling object. This is part of the modeling sub package. So under the modeling set of functions, there is literally .model, which will, in the same way as .survey makes a survey class to hold all of your survey information, .model makes a modeling class to hold all of your modeling information. It takes three things. First, you have to give it a name. In this case, giant planets _ Kepler is roughly a description of what we're going to do. And then we can also give it that criteria dictionary, which specified the stuff that we're going to look at. And then the surveys that we're going to use. And I say surveys plural because later on we're going to use multiple surveys. Questions so far? How are we feeling? We good? Yes. Sorry, could you say that again? Sorry, what was that? Great question. Okay. Yeah. So looking at this output of the modeling cell, there's a line that says like some number of planets were dropped. Um, every now and then you get planets that are gross and annoying and behave poorly. And sometimes that is because their data quality is like really bad. And other times it's because they are like so uncertain that it's not worth including them because they only make things take longer, but they don't give you information. So those are like two examples of why we would get rid of planets. It is somewhat standard process to make like quality cuts on your information and like what types of planets and stars you are including. And so that line contains some of that information. Yeah, so if you do run that cell to give a brief description, there'll be a line that says like we're getting this particular survey ready, and then it will tell you how many stars and planets it uses, and especially if it's cutting any stars and planets. Other thoughts, questions, concerns? Is that part of the criteria? No. So specifically the number of planets here that it refers to are things that match your criteria. And then things that get dropped are stuff that had bad quality information, but otherwise matched your criteria. There's like thousands of planets with Kepler, but in this case, we selected a really small subsample of those. So it only tells us that there are like 150-ish that were relevant, and then we got rid of 4 of them because they were bad. Sick. Okay, as a warning, I guess, as a brief like descriptor of how we made this code work for the workshop, a lot of the models that you will see today have been pre-run, meaning that we did the computationally intensive part ahead of time and then gave you a sort of pre-run version of that so you can see what has been done without having to wait a few minutes for it to actually be done. All of that information is dependent on what the models are named. So for example, here we have specified the model as giant planets underscore Kepler. And if you changed that, it would think that you're doing a new model, and then it will try to run it for itself. That is especially useful if you're doing like group projects and you're trying to make your own models. But for the purposes of this particular session, I would advise keeping the names as is so that you don't have to wait for things to run. Cool. So once that modeling object is created, there's a couple other things that you have to do to like specify the type of model that you want to fit. I mentioned describing a shape function that actually describes like what is the literal form of the model that you're going to make. So this is quite literally just a parameterization of how trends change with different planet properties. And there are 2 Pythonic things that you have to, like 2 Python functions that you actually have to make. There is a shape function itself, which just as I showed you, the occurrence rate changing as a function of semi-major axis raised to some slope. Here we have coded that exact function to have x, the semi-major axis, raised to some power law slope that I called beta. You could call it whatever you want. And then there's this second secret thing that we haven't talked about yet, which also describes what is going on with planet size. So in this particular exercise, we're really just focused on the semi-major axis distribution. And so enforcing this part to say size raised to the -1 means that we're going to adopt a uniform or flat distribution between occurrence rates and planet size. You'll see that later, a little bit later, and understand why that's like useful. But if anyone's wondering, like the reason it's -1 and not 0 is because these things are defined in log space. So the difference between log and linear space is a factor of 1 in your power law slopes because calculus, I guess. So generally, if you want something to be flat here, we'll adopt an exponent of to the -1, just to clarify. So that describes your shape function, and you'll notice the calls are x and y for the planet's separation and size, respectively. And then this thing that I call f-param, which stands for free parameter vector. So this quite literally is just a package of whatever free parameters your model has and will use and try to optimize. The other thing that you have to do, and is a good idea to do, is to make a prior function. So if you've never worked with like Monte Carlo processes and optimization, one extremely handy trick to make things not take a billion years is to define priors that are like relative constraints on parameter values so that your bits don't go off to infinity or don't go into like unphysical spaces or things like that. So for the most part, we are adopting the most basic kind of prior that you can, which is saying that you want a number to be not too big and not too little. So these are almost always just ranges slapped onto values. In this case, I've said that I want my occurrence to be larger than 0.01%. And I want my slope to be somewhere between plus and minus 10, which most slopes are like 1 to 2. So that's a pretty generous range, but just as an example of how loose you can make these things to help out. Nevertheless, you do have to define a prior function, and really all this does is check if your free parameters are within a particular range, then it's not going to tank your likelihood function when you fit a model. But if they are outside of that range, it is going to tank your likelihood function and say that this model is really bad and we don't like these values for these free parameters, so please use something else. These two functions you're going to see a lot. We're going to change them because they're like different types of models, but this sort of notation is like the one hard requirement for how to run things here. So are there any questions, comments, concerns on that front? Yeah. Okay, two parts. One, why a power law in this particular case? Because it kind of looks like it. This is like, I am an occurrence rate modeler, so I talk about modeling a lot. But the inverse detection efficiency method is extremely useful to tell us what types of models to fit. And that's like 80% of the reason we use it. So in this case, we did this exercise of like plotting the inverse detection efficiency values to see what the shape of this trend was. And it's like kind of a line. So maybe we'll fit a line to it. You had a second part of your question that I immediately forgot. Yeah, vibes. So the first part of to repeat the question, like if you have a new survey that you've never seen before and you're trying to figure out what priors to set, how do you figure out your priors? Vibes. For the most part, you look at the inverse detection efficiency method to get a feel for both what kind of function you might want to fit and then what values you could fit to that data. It is somewhat of like a learned process of like, I can look at a power law and roughly guess what the slope is at this point, but you could also like hard code it, like literally use the shape function that you made to fit this model. And before you actually fit the model, test it out with a couple different random values for your free parameters to be like, what does this really look like? That's sort of the process. Sometimes the inverse detection efficiency method will also give you information of like, if you just compute it over one bin, in principle, the occurrence rate that it gives you should roughly be the same as the F0 parameter that you're actually trying to fit here for the occurrence rate. So ideally, those numbers are the same, which also helps you to inform the priors that you could have. Yeah. So like the question is basically why do the hard way and not just like least squares regression or like a chi-squared reduction type fit or like any of the pre-existing fitting a line functions in like SciPy and things. We'll get into much more complicated occurrence models in a bit. That's sort of the back part of this session. But in either case, there are like, if you were to try fitting a line with like curve regression, you would probably have to do that to the data points from the inverse detection efficiency method, which are a roughly incomplete view of the occurrence rates. They are sensitive to the number of bins that you have. So changing how you're binning your inverse detection efficiency data would also change the number and values of data points that you would use. Whereas a model is fitting to the entire underlying planetary population. And I'll give you a description of how that works in a second. So modeling the hard way is much more robust because it's not sensitive to like choices of bins. It's not sensitive to like biases or quirks in, for example, survey sensitivity as a function of those bins. And it is more generally capturing the distribution of planets in the underlying sample more so than like an arbitrary selection of bins does.
So I just wanted to mention that there are other packages out there, also the early version of packages that we developed at the University of Arizona that did exactly what you are saying. So fitting on the inverse detection efficiency method, simple power laws, right? But this code is more powerful in that it looks at the underlying, but you can also, those codes are also on GitHub. So I'll mention it tomorrow. So you can first test on those and then use this better code.
Okay. So to like recap that discussion, there's stuff the inverse detection efficiency method can't do, and modeling is like a fancier version that does the stuff the inverse detection efficiency method can't do. It is harder, and you have to make some assumptions about like the type of functional form that you're going to choose, but generally, it helps us do a better job of like actually fitting planetary populations. Cool. Question. Absolutely. So the question is like, can you keep the same model name but change stuff and have it fit a new model? Yes. There is a keyword that will sometimes get spit out at you if you like break things really hard. But in a bit, I'll show you this function that's all about actually fitting the model. And in particular, you could include the keyword of overwrite equals true, which will do exactly what this question asked and like reset the model, fit a new one using the same name and or parameters. But I'm not going to do that because it takes some time. Okay, so before we actually like fit a model, I wanted to explain how the model works. If you didn't get the like parameterization and like math of it, another way that you could think about things is that we're essentially trying to constrain a probability density grid, which is a fancy way of saying a thing that tells us how many planets should be at what particular separation and size. So this is an example of like what that model actually looks like. This is the two-dimensional probability grid of the broken power law that we just fit. So this will show you that occurrence rates are increasing as you go towards farther sizes, but also we adopted it to be uniform in planet mass. So there's no other variation. There's like no reason to have a vertical axis here. So as a brief description of like how we actually optimize these models and what happens inside a Monte Carlo process. By the way, we're using an MCMC or Markov chain Monte Carlo process to sort of iteratively optimize the free parameters for the model that we're about to fit. And in each iteration, the sort of shindig that happens is as follows. First, we'll use that parametric description of the planetary population to generate a sample of synthetic, very fake planets in proportion to whatever model it is that we are currently working with. So the current MC iterations, free parameter vectors, and functional form that we have defined tells us how many planets we should make and where we should make them. And then we use survey sensitivity metrics to basically simulate which of those planets would be detectable. So if we have a whole population of planets that are like actually out there in the universe, and then we pretend that we are observing them with the Kepler mission using the sensitivities that Kepler has, you are obviously not going to detect most of those planets. And so this gives us a you could call it a synthetic observed population of planets. That is, none of them are real, and we have simulated the process of their observability to guess what we might have seen. And then we actually compare those with the Kepler sample. These are real Kepler planets that I've plotted in black to try and guess on a couple different metrics. Have we done a good job? Is this particular model producing the right number of planets at the right separations and sizes in proportion to stuff that we saw with Kepler? I could get into the statistics of like how we actually make that comparison, but it is very similar to a lot of other statistical metrics that you might have heard of, like a chi-squared metric that tells you if you have the right number of things, or like a KS, like a Kolmogorov-Smirnov test, or an Anderson-Darling statistic that compares the distributions and number of those things. It's the same sort of basic principles to say, how good did we do at recreating the observations? Questions on like the philosophy of fitting a model? Okie dokie, let's do it. So if we hop back to Colab, there is quite literally a function called fit model. You'll never guess what it does. So you can give it the same modeling object that you have created, which so far only stores the name of the model that you want to make, the criteria for the planets and stars that you will include, and the survey data that you will include in it. And then also give it as part of this dictionary that describes the shape function and prior function. We can use those Python iterations that we just made that describe how we want stuff to behave. And then to go back to Alex's question, an initial guess, sort of a first pass at what those parameters might be. When in doubt, you could just copy some of the stuff that's in this notebook. Nothing will ever go wrong if you just pick one for a lot of these numbers. So like if you don't know what to make your power law slope, just make it 1 and see what happens. Or you could do it like if you do a model and it takes a while, but you get a guess at the end, you could redo the model, but make that guess your initial guess for another model, that sort of thing. And then this last line is a bunch of like optimization parameters. If you've never used MC before, I'll give you like a brief description of what these are doing. So N step is the number of steps that our Monte Carlo process will run for. These are like individual iterations of like trying a particular set of free parameters, seeing how good it is, and then moving on to the next one. Then N walk is the number of walkers that are individually doing that process. So Markov chain Monte Carlo refers to having a lot of these like chains of steps going on at the same time. So this just specifies, both of those things just specify like how robustly are we actually going to do this. And then there's this thing called N draw. Don't worry about it too much and don't change it from 2. To give you a brief description of what this is doing, we talked about like in Kepler and transit case, the reliability of samples of like how much we trust that these things are real planets. There's no perfect practice to actually incorporate that information in a modeling process. So one thing that you can do is just do your model a bunch of times, but change how often you include things based on its reliability. So for example, if I had a planet that was like 50% real, I could run a model twice and include it one time, but exclude it another time, and then put those results together to approximately contribute the weight of that planet as like half the weight of a planet that's included every time. It's gross statistical philosophy. And for the most part, we would set this number to be really high to like robustly sample things, but we've got a week. And for this particular session, we've got like an hour. So we're keeping things short and roughly simulating that process. Okay. Once you have all of that set up, you can actually run this function and it will go, I'm bad at my own code. You can run that function to check if the model already exists by the same name and with all of the same specifications that we've outlined here. In this case, it already does exist because we ran it for you. But in like the group projects, for example, the stuff that you're trying to fit probably won't exist yet. So you'll be able to actually like see how this works as a like brief precursor. It'll spit out an MC progress bar that's saying how long things are going to take, and then you can walk away, grab a drink. But yeah, that's what you can expect when you're doing your group projects. And I'll show you an example of that happening live at the very end. But for now, let's use these pre-run models just so we can keep things moving along. Questions, comments? How we doing so far? Thumbs, more thumbs than last time. Let's go. Okay. Sick. Let's keep it going. Once your model has been run, then you can start to check out some of the stuff that comes out of that process, and the like processing of the MC outputs and like preparing all of your results is all nicely wrapped up in a .prepare results function. And I should clarify that a lot of these functions are happening onto the model class itself. So once the model is run, all of that information gets sort of stored inside the modeling class, and then you can keep using that object as it is named as you go forward. So what prepare results actually does is like put together the free parameter vectors from Monte Carlo. It like simulates what the occurrence distributions should look like for your best fit model, that kind of thing. And one of the easiest ways to gauge how you did is to make a corner plot. So the free parameters that are tried during the modeling process will all be included as this .samples attribute. And so if you use, for example, the corner package or your favorite histogram maker to look at the distributions of those samples, you can actually see the outputs of your free parameters. In our case, we had two free parameters, one for the occurrence rate overall, and then one for the power law slope. In this particular example, those are extremely well constrained as nice, pretty, almost normal distributions. So that's good. If you are doing your group projects and you get scrunkly histograms that are like not nice, evenly peaked Gaussians or things, those are not bad. They are interesting. And so I'd encourage you to like, if you get those, think about like why. Like if it is completely flat, that would mean your parameter is largely unconstrained. There is no best fit value. And what does that mean within the context of the data that you have? And if there's like two peaks, why is that interesting? That sort of thing. Another more interesting way to look at things rather than just talking about free parameters themselves is to consider what they actually look like in the model that you fit. So there's a series of functions that work pretty much the same as the plotting occurrence rates from the inverse detection efficiency method, but now plotting using the model that you came up with. So also part of that plotting subpackage, there is a function called plot model occurrence 1D. You'll note when we did it with the inverse detection efficiency method, I think it was survey and not model. So here we're using the modeling object. But once again, you can specify like what is the dimension that you want to plot over. In this case, the X or semi-major axis distribution, and how many bins do you want to use. And then it'll make plots like you've been seeing in my slides that show you the inverse detection efficiency rates compared to the actual model that you get. So the black line here is the like median or like most common best fit of your MC process. And then the gray uncertainty envelope is coming from the sort of spread of your free parameters, the spread of the potential model values that you could get, and is sort of an approximation of how good your model is and how good it can be constraining things. How do we feel about this? Are we good? Do we understand like where this line comes from? Sick. Cool, cool, cool. So I teased previously that we were also talking about the mass distribution and that we had fit a flat distribution. So this is the first time I'm showing you, sorry, not mass, size. This is the size occurrence distribution of Kepler's giant planets, which I have tucked under the hood for now. But this is your first glance at it because, again, these models are at least two-dimensional. They have a component for the separation, which is this power law that we fit, and for the planet size. So in this case, Kepler's giant planets are like kind of flat. As a little exercise, you can also try to like change the number of bins here to see how reasonable that approximation is. And if you do like way less bins, it's also kind of flat. So for the most part, in this particular case, flat is good enough. You could fit a more complicated version, but then you would have more free parameters, which always makes your models have a harder time and sometimes reduces the amount of statistical information that they actually have that is useful. So generally, when it comes to occurrence rate modeling, adopting a simpler functional form is typically better, but you can also test that out in some of our group projects. Okay. This takes us through the exercise of modeling with one survey. And I'm going to get into modeling with multiple surveys. It's going to be mostly the same, but I want to see how we're feeling. If we have questions about like how to fit an occurrence model, what the heck is going on? How are we doing? Thumbs, thumbs. Question. Yeah. Let's do a recap of how we're actually fitting to the underlying planet distribution. So I think I did a bad job of introducing this plot on the left. This is like an example of what your occurrence model actually looks like. So previously you've defined some, where am I going? What am I doing? Previously you've defined some functional form that describes how your occurrence rates change with different properties. And this is sort of a visualization of that as like a probability field, a probability density grid. And so in a given Monte Carlo iteration, we'll draw planets out of that grid, and then we'll simulate their observability to determine like which ones could have been observed by a particular survey. And then using a couple different metrics, we'll compare that to the actual observed sample of planets. And then this gives us like almost a goodness of fit to tell us how good of a job we did. Like, is this particular iteration of a model good? Is it better than previous iterations, or is it worse than previous iterations? And we do that through something called a likelihood function, which will tell you you have a more likely model if it's doing a really good job and a less likely model if it's doing a really bad job. And then using that determination, we'll decide if this is like a good set of free parameters to continue trying to constrain, or if we need to go somewhere else in the parameter space. Does that clarify? Perfect. Other questions? Sweet. We're gonna get into some like slightly harder stuff, and I know that I've been yapping for like an hour. So I wanted to give folks like 5 minutes to like stretch, grab some water, use the restroom, stretch your brains, and we'll reconvene shortly. Plug in the great observation.
I was wondering, so how actually do you do the comparison? So you kind of um, mentioned to, well,
I glossed over it, yes.
yeah, you glossed over it, but
Yeah.
is it like nearest neighbors kind of?
So it is the full version that it's a Poissonian likelihood function that compares the first compares the two numbers, so the number of observed planets, the number of like synthetic observed planets, and if those are at all close to each other, like within order of magnitude, that's sort of the first step.
Yes.
And then the second check is actually looking at the underlying distribution of things, which are like integrals. So you formally integrate your probability density function and integrate the planetary population to see if those are giving you like similar CDFs or the cumulative distribution functions. And then that is secondary metric. So really, Poissonian likelihood functions.
So marginalizing basically over the axis, and then the third would be to
Yeah, so
put distributions at every point and see.
yeah, Poissonian likelihood functions are like the level above KS tests, where KS tests have like marginalized the distributions. Poisson likelihood function is looking at all dimensions simultaneously.
But so do you put a Poisson distribution every
Hey. All right, we're back on the grind. Hope everyone feels a little bit refreshed. We are now going to shift gears and start talking about modeling with multiple exoplanet surveys, which is really sort of like the bread and butter of this code. It's why we made it, and is kind of a new-ish thing. So I wanted to give you a little bit of background on like why it's useful and what we're going to use it for. I showed this plot yesterday, looking at the distribution of known exoplanets, just to highlight like where different biases fall. So my example was that like really close in planets are mostly covered by transits, but transits are not cutting it outside of like 1 AU. So we have to rely on other methods like direct imaging at really far out separations, or like long-term radial velocity or gravitational microlensing to help us probe the sort of intermediate separations of planets. You also heard a lot about astrometry, and that will also probably fall into like the middle of this plot in like a decade. But we're not there yet. And microlensing is also hard, and sometimes it makes me sad. So for this workshop, we're just going to be talking about transits, radial velocity, and direct imaging. But all of the principles that we're about to talk about, the stuff that you're about to learn, can apply to any combination of detection techniques. And also, we built this code to work with any combination of detection techniques. So while the version that you have right now only has 3 surveys from those 3 methods, the full version may have some more stuff, and also be updated down the road as we fold out or fold in more surveys, more data releases come out with all the like metadata that we need to do demographics. So in this particular exercise, we're going to be talking about the distribution of giant planets using multiple methods of exoplanet detection. And I want to especially introduce you to maybe, I think, the first work to do this and find something that was really cool. So there was some great work by Rachel Fernandez and company like 6 years ago, time has passed, looking at the frequency of giant planets from 2 different methods and realizing something that you can't find with just one method on its own. So this plot, we're going to look at planet frequency as a function of their separation. Semi-major axis is on the bottom, orbital period is on the top as like an equivalent proxy, and then there's some solar system planets for reference. So one thing that Rachel found was that if you look at Kepler data for giant planets, there's this really well-known sort of increasing trend, the thing that we just fit with a single power law. But if you also use radial velocity data to study stuff that is farther out than what transits can measure, you find that it doesn't go up forever, that there is eventually a turnover, and then the distribution might start to go back down. For a while, all we had was the stuff on the left, the transit distribution suggesting that giant planets are more and more common at larger and larger separations. So people were like, yeah, direct imaging should have like infinite planets. And then it turned out to have like a couple planets, which is a smaller number. So we realized that something had to be different. And only by using multiple demographic surveys did we realize that, oh, it probably actually goes back down eventually. Another thing that's really interesting is that the shape of this distribution tells you a lot about giant planet physics, which I'm using as like a catch-all term to constrain details about their planet formation and their migration processes and a whole bunch of other things. So on the bottom, which I think were also some of the like suggested readings for this affair, there are some papers that have looked at the distribution of giant planets with 1 or more surveys and are trying to figure out what the shape of this distribution is. What does it tell us about planetary physics? But for our purposes, we're going to think about it in sort of 2 halves. A half that is at close-in separations, like before this turnover or break, and then stuff that's going on after that turnover or break. In particular, where that change happens, like where the shift is, could tell you about like planet formation. It maybe coincides with this thing called the snow line, where there's like a sharp change in the solid density of your protoplanetary disk environment, because you can start to freeze things, which means you have stuff to make planets out of. So it could be that giant planets are really common at the snow line, which tells us about how they are forming and what they are made of. It could also tell us about a point where they like pile up in their migration journeys. Perhaps they form much farther out and then all sort of move in, but like stop at kind of the same place. So we're going to get into trying to understand and then constrain this distribution and see what we can learn. Ooh, actually, before we do that, before we go to Colab, I want to briefly introduce to you the 3 surveys that we're working with. And I also just got a question about like, where does the completeness come from? So in all of the surveys that you're about to see, the completeness metrics have come from the original survey teams who were doing their own metrics and estimates to try and constrain their own survey sensitivity. You heard a little bit of it about like injection recovery tests this morning, the idea that we like inject a fake signal into data and then run it through our planet detection pipeline to see if we can recover that, which roughly tells you how good you are at actually finding that thing. That is a very common way to constrain survey completeness. But these completeness metrics that are stored in the software package, they've all come from the incredible work of these various survey teams. I think they are cited accordingly on like the workshop page. But if anyone has like exact questions about where these particular metrics for surveys come from, hopefully that answers things. And I'm also happy to dive a little bit deeper if you want. So you've already seen the Kepler sample. We've heard a lot about it today. This is a brief depiction of the giant planets and the survey sensitivity that we're going to use. Now I'll introduce to you some other samples. We'll have the radial velocity data set from the California Legacy Survey. You saw this at the very start today, but this is now zoomed in on just the giant planets. And then we also have some data from direct imaging. This is coming from the SHINE sample of exoplanets. You'll note that there are like 6 planets here, as opposed to probably a couple hundred with Kepler and like tens of planets with radial velocity. Why is that? We are in a regime where direct imaging planets are not the most common in terms of detections for 2 reasons. One, I said that we are focusing on sun-like stars, and I gave you a particular mass range that caps out at like 1.6 solar masses, which is like on the low end for most direct imaging detections. Direct imaging favors things that are hot and bright and tend to be around more massive or brighter stars. So this is sort of the bottom of that barrel. And then also direct imaging is like really hard. So there aren't a lot of direct imaging planets in general. I think the total number of planets found with the SHINE sample is like 15 or maybe 18 or something, as opposed to Kepler's like thousands, which maybe sets the scale of like how vastly different these techniques are. But nevertheless, we have some data to work with, and work with it we shall. So these are the 3 data sets that we're going to become intimately familiar with during this modeling process, just as an introduction. Okie dokie. If we hop back over to Colab, we are now we're in the section talking about modeling giant planet occurrence with transits, RV, and imaging. And once more, we're going to see our friend, the criteria dictionary, that looks almost exactly the same. First, we'll specify the size regimes that we want to focus on for these planets, and I'm going to do it in planet mass space. We're going to select things that are within an order of magnitude of a Jupiter mass. So if you've never like worked with AstroPi units before, this is just a line of code to say that we want things between 0.1 Jupiter masses and 10 Jupiter masses. But because all of these tables are formatted in units of Earth masses, then I go through a little conversion to swap those limits to the corresponding Earth mass units. And then, just as we have done a couple times before, we'll define our criteria dictionary to say the types of planets that we're going to look at. In this case, we'll be modeling as a function of planet semi-major axis and mass, swapping our size dimension, and I'll get back to that in a second. And then picking a range of those things between those 2 mass limits I just set, and then looking between anywhere from 0.01 to 100 AU, which is like 5 orders of magnitude, way beyond what you could hope to constrain with any one particular survey. But with multiple surveys, hopefully we can figure something out. And then once more, these bottom 2 lines will remain unchanged for now. Okay. So once more, you'll have to load in the survey objects. So far, we've only been doing one of them at a time, but now we'll do all 3. The Kepler and CLS lines are exactly as you have seen them before. Again, going through that process of translating Kepler's survey sensitivity from the period plane to the semi-major axis plane. But with CLS and with SHINE, their sensitivity metrics are already defined in terms of semi-major axis, so we don't have to do that. But as always, you'll just read them in using the corresponding survey names. And then, as a brief little glimpse to go back to some of these questions of like, how do you get a feel for what these distributions look like and the types of models that you should fit, we can rely on our friend, the inverse detection efficiency method. So these three lines are all doing the same thing, but with different surveys, each calling the same function to plot the inverse detection efficiency method using the same bins and the same criteria specifications, but for each of those surveys. So for the Kepler data, which is in blue, we have that same increasing trend that we've now seen a couple times. And then these two other additions to the plot are kind of new. You've got radial velocity data in orange and the SHINE sample in green. I'm going to hop over to PowerPoint and give you a brief disclaimer as to why the distribution from Fernandez et al. From a couple of years ago looks different from the distribution that you just saw. There are two things. One, times have changed. We are using a different, slightly more robust radial velocity survey that has more stuff to work with. I think it's like a factor of 10 more stars and planets, and also like a more updated version of Kepler. We are constantly improving how we work with Kepler data. And so what Rachel had in 2019 for that paper is a slightly older version. And you'll also note that the radial velocity stuff in this older version goes like way closer in, whereas the stuff that we have today cuts off at like 0.1, 0.2 AU. This goes back to that disclaimer I gave you at the very start, that the version of this data that you have now has been truncated a little bit for educational purposes to get around some hard statistical stuff that is involved with the California Legacy Survey at like really close in separations. I'm happy to talk about that offline or if anyone like really wants to get into it. But for now, just hopefully vibe with the fact that we are using a sort of truncated version of the data set where everything outside of that point, so the stuff where we do have orange data, the good information, is like extremely high quality data. So we don't have to worry about there being any like weird quirks or statistics or things. Sweet. So this is like a brief glimpse at what the giant planet distribution looks like. You may also notice that the shape appears a little bit different. Back in 2019, there was this evidence that it goes down pretty quickly after you pass that turnover. But nowadays, with these updated distributions from a newer radial velocity data set and adding direct imaging, maybe it doesn't go down so much as plateau. And I want to stress that this is a perfect example of how demographics is ever evolving. Sometimes we think we know something real good, and then we get new information that says, in fact, it was not so good. And so a lot of the stuff that you see today or in any of the talks this week are probably updated versions of things that we thought we knew like 10 years ago and will probably also be different 10 years from now. This is sort of the ever-evolving process of improving the ways that we do population statistics, getting more information, and getting better at correcting the biases in that information. Sweet. So I gave you a little overview of like how we actually fit a model to a single survey, this idea of like simulating a planetary population based on some functions that describe how common planets should be, and then comparing those to the observed distribution. But I also want to give you like a little bit of statistical theory on how we do that with multiple surveys, because those comparisons can get very complex very quickly. And I'm going to hopefully convey this in a way that is not complex very quickly. I am constantly a visual learner. So I'm going to use an example of like flipping coins. This is maybe like intro statistics type stuff, but the odds of flipping a coin twice and getting heads on both of those flips is by this thing called Bayes' theorem. The odds of getting heads on one flip times the odds of getting it on the other. This is the sort of basic statistical principle that the odds of observing two independent events is just the odds of those events multiplied together. For talking about exoplanet surveys, we're going to use this exact same framework, but now the observations that we're making is that a particular model matches a particular data set. So in other words, the odds that you can fit one model that matches two particular survey data sets, in this case, I've just included Kepler and TESS, is roughly the odds of that model working for one survey times the odds of it working for the other survey. So I made a brief mention of this thing called the likelihood function, which is like a metric of how good your model is at matching your data. And so in this code and in this like philosophy of combining data, we're fitting that model to each of these survey data sets independently, but it's the same model. So we're trying to evaluate how good that model is doing at matching all of the surveys at the same time. On a scale of thumbs up to thumbs down, how much of that stuck? How we feeling? Was that a good explanation? Okay. I saw several thumbs sideways, which I'm going to take as decent. If none of this stuck with you, don't worry about it. We're just throwing stuff at the wall and seeing what sticks. But in this particular case, we're throwing it at like multiple walls and hoping it sticks to all of them. One other thing that we haven't yet talked about is that transits are weird in the grand scheme of things because they're kind of our only method of discovering exoplanets that measures planet radii, whereas a lot of other methods measure some metric of planet mass. So like radial velocity, for example, is measuring the minimum mass of the planet. Direct imaging, kind of measuring the mass through like a somewhat arduous process of measuring the brightness of a planet. Like microlensing measures the mass ratio of planet to star, but transits are perhaps unique in that they measure planet radii. So when we talk about defining an occurrence model that works for multiple surveys, we do have to define what dimensions we're going to use for that. And in the notebook, I said that we were going to use planet mass, but that maybe causes a problem because what do you do with transits that are not measuring planet mass? So analytically, the occurrence functions that we're going to define will be functions of planet semi-major axis and planet mass, but then we'll jump through a hoop to work with transit data. That hoop is the mass radius relation. So there's this really handy thing where you look at empirical data and it turns out that planets of the same size are sometimes roughly the same mass, which means that you can try to fit some relations that describe how those two properties change and relate to each other. So for our purposes, we're going to handle the occurrence rates defined as a function of planet mass, but then we're going to rely on this mass radius relation so that when we work with transit data, we'll pass our occurrence model through this mass radius relation in order to compare it with transits that are measuring planet radii. This is, for this particular case, we're going to be using the Chen and Kipping mass radius relation, which is somewhat famous. And again, is just this idea that like if you look at observed planets, which are all of these like black points, they roughly follow some trends that you could roughly fit with some power laws. And so if you have like you're fitting an occurrence model that tells you how many planets you should have at a particular mass, you could simulate those planets at that particular mass and then pass all of them through a mass radius relation to figure out what their radii should be, and then compare that to Kepler data or transit data, which is measuring planet radii. This is gross and a somewhat arduous process that is, for this workshop, extremely computationally simplified so that it doesn't take a really long time. But in general, this is like one of the approaches that people have come up with for how to combine transit surveys with other stuff. There's probably also other ideas, but for the most part, this is the one that people have been using. So it's the standard that we'll adopt today. Yes, so this relation is probabilistic in nature in that it gives you a guess as to what a planet of a particular mass should have for a radius, but there is, of course, a range and there's a probability that it might not have that exact value. How does that affect your occurrence rates? The short answer is that it would affect your occurrence rates if you only did things once. Like if you just did a single iteration where you come out of this mass radius relationship at just one value that happened to be from a random probability distribution, then yes, it would be very different from another case where you do it a separate time and come out of this relation with a different value. But if you do it like 100 million times, hopefully you capture that distribution pretty well. As a general rule of thumb, the uncertainties in occurrence rates and the distributions that we're trying to model are like way bigger than the uncertainties of any particular mass radius relation. So it is generally considered to be like a second, perhaps even third order problem. But if you simulate anything enough times, you can roughly solve those problems.
Is there play are most of these observations? Is there a range of 50 light years, or within a certain defined sphere? Occurred to me was since you have mass and you have a radius, if you produce the density, is density of the bodies be one in terms of how they affect the wobble?
Okay, I'll tackle these questions in two parts. The first part was asking like how far away are these planets? It varies. With Kepler, most of the planets are like on the order of a kiloparsec away. But with radial velocity observations, like the California legacy sample tends to be closer. There's some overlap with Kepler. And then direct imaging is largely a function of what you can find. So I don't have like great numbers, but there is a spread, if that helps to answer your question. And then the second part, like if you have mass and radius, could you do things in density? Yes, but we don't have mass and radius. So for like any one of these surveys, you will only ever have one of them because like with a radial velocity survey, all it is measuring is planet mass. And that's the thing that happens as part of the survey. You can do follow-up later to like get transit observations and determine the radius, but those aren't coming from like the same survey. So sometimes those constraints can have very different like sensitivity issues that wildly affect your bias corrections. So generally, as a rule of thumb, demographics hinges exclusively on native measurements. We only work with the stuff that actually comes from the observations. In a perfect world where you have mass and radius for everything, then yeah, you could probably measure things in like the planet density plane, but that is far from the world we live in. Yeah. Stuart says 3,000 light years to a parsec, or vice versa. That Ilaria, go ahead.
Is your question because you are concerned that if you sample a population far out and the population close in, then you are not sampling similar planet? Is that your question? Because if that, maybe you can bring up again that paper by Rachel Fernandez, right, that we wrote in 2019. The idea to compare Kepler and radial velocity for giant planets was exactly that, to see if they match in the period range that they both cover, and they do. So that's not a concern.
Sweet. Other questions? Okie dokie. I brought up the mass radius thing just to like explain what sorcery is happening, but that sorcery is happening like behind the scenes. That entire process is wrapped internally in the code, so you never really have to look at the mass radius relation. It is maybe a part of some of the group projects, which I can come back to. But that whole process and the whole simulation process at large, with all of that like probabilities and coin flipping stuff, is all tucked sort of behind the scenes so that you don't have to do gross statistics on your own. Okay, so now that we've talked about how to model multiple surveys, let's actually do it. As we did with the power law exercise, where we fit a single power law to Kepler, we're going to try and now fit a broken power law to the distribution of giant planets. A broken power law is just two power laws taped together, and they change between one slope and the other at some break location. So one way to write that Pythonically is in this broken power law shape function, where once again, this argument we'll have the planet size and separation, in this case, the semi-major axis and planet mass, respectively, and then the free parameter vector. A broken power law requires 3 parameters on its own, so we'll have 4 total, 3 for the power law and 1 for the overall occurrence rate. This, once more, to get it out of the way, we'll adopt a flat occurrence mass distribution, just like we did with the single power law with Kepler data. But then, as to like explain what the heck is going on here, we have a where statement that asks if the semi-major axes are less than or greater than a particular value, we'll use one slope versus the other. In this particular case, we're going to define where that break happens to be in log semi-major axis, because we're working with like a really big range of values. I said that we're using 5 orders of magnitude. And if you tried to fit where that value is linearly, you're going to have a bad time. So it is instead easier to try and find out where that happens by fitting the log of that value. So a lot of times you'll see it translated as like 10 raised to the power of that value to like figure out what the actual physical units of that is. But for computational purposes, we'll use the log value. And then just as we had with the power law function, we'll have a prior function that puts some ranges on the stuff that we're going to use. For the slopes, we'll use the same very loose ranges that are like way wider than what the slopes will actually be. And we'll use the same limit that our occurrence rate should hopefully be a positive number that is a little bit greater than a really small number. But then to get back to, I think, Alex's previous question of like, how do you put realistic ranges on things? As an exercise, we're trying to fit where this break location could be. So if we look at the distribution from the inverse detection efficiency method, we have a roughly increasing distribution up to somewhere around 1 AU. And then it's pretty clear that we're using a different slope after that, certainly by like 10 AU. So in log space, you could put limits on that of like 0, which would be 10 to the 0 or 1 AU. Up to like 10, which would be 1 in log space. But in this particular case, I've adopted an even looser range just to roughly fit within our domain, but not go outside of the domain so that we don't fit things we can't fit. But that's the reason why these constraints on this value, that's where they come from. They come from trying to fit within the plot and a somewhat physical neighborhood of where we think that break might happen based on the inverse detection efficiency method. Questions on either of these functions, what they're doing, the kind of model that they're going to fit? Okay. Are we like, is it appropriate to use a mass radius relation that is like based on observations to try and then constrain other observations is like the gist of this question, I think. It's good enough. There are theoretical mass radius relations out there that are like kind of the same as the empirical ones. So to like first and maybe even second order, they're good enough. But it's also worth noting that these are like very different sets of observations, right? We are like the mass radius relations from Chen and Kipping. I don't remember exactly where this particular sample has come from, but there are plenty of other mass radius relations out there that are like more modern, shiny, fancier, that use just everything in the Exoplanet archive with like a measured mass and radius. So like literally everything we have ever found that has those 2 sets of observations. And that is often an extremely different sample than the stuff that we are actually doing demographics with, because demographics strictly come from like uniform surveys, whereas the archive is a host of everything we've ever found, including trying really hard to find particular planets, which are like demographically unusable. So it's like a reasonable approximation to use these 2 things. I'll give you like a spoiler for future works, that this process is largely robust to the kind of mass radius relation you're using. So like if you are using a theoretical relation or an empirical relation, or even a relation that is based on the data that you have in these surveys, you will almost always find similar occurrence results, because the mass radius relation is like a tertiary problem compared to the actual occurrence rate problems that we have. I hope that clarifies things. other cues? To expound on Ilaria's point, yes, the plot that is on screen right now, this is a empirical distribution of plotting planets that had masses and radii. It is not an occurrence rate model. This is strictly fit in some lines to some points, which we can then use to inform the kinds of occurrence rates models that we want to constrain. But this is the equivalent of plotting solar system planets on a plot and then fitting a line to it, whereas occurrence rate modeling is like trying to model the solar system. Great. Other questions? Okie dokie. I should have given this visual earlier. This is what a broken power law looks like. Spoilers for the stuff that we're about to do. But when I was talking about those two different slopes, the first of those two slopes is whatever's going on before the break. And then the second of those two slopes is whatever's going on after the break. And then roughly where that break falls is the transition between the two. We'll come back to this distribution and explain why it is the way it is in just a moment. Okay, so hopping back to Colab, once you have defined those two functions, you can go through the exact same modeling process, but now using data from multiple surveys to fit this slightly more complicated model. There's a question earlier about like what F0 does, because you'll notice that it is not used in either of these like shape functions. So where does it come into play? The short answer is behind the scenes. We walked through this example of like simulating planets to then compare to observed data. F0 is the parameter that tells you how many planets to make. So it doesn't show up in the actual like shape of the occurrence distribution, but it does show up everywhere else. And that everywhere else is behind the scenes, tucked in these .py files. But as a brief clarification, that's what it does and what it is used for. Okay, so just as we did before, we can make a new modeling object that has a name. In this case, we called it giant planets with no underscore Kepler, because now we're using multiple surveys. So you will also pass it all of the surveys that you wish to include, as well as that same criteria dictionary that once again defines the types of stuff that you're going to be working with. And then you can run through the process of actually fitting that model. Again, we have pre-fit this model for you, but the outputs in this cell, this is again describing like which surveys are being used, how many stars and planets they have, and if you have to get rid of any because they have so-so quality, and then going through the process of fitting the model, or in this case, realizing the model has already been fit for you, and then being able to access that information. So just as we've done before, we can use the prepare results function, and you will immediately notice that there are some errors here. These errors are often coming out as like warning mc.autocore or other things related to the MC process. If you were doing your own real science, you should always pay attention to these errors. But if you're doing a workshop and only have 2 hours, we're going to ignore them. What these errors are is telling us probably that the MC process, the like model fitting, did not happen for long enough, that we needed to run a longer model to thoroughly probe the sample space of what our free parameters could be, to ensure that those free parameters hopefully converge, that kind of thing. But doing that takes longer time, obviously. So for this case, we gave you a shorter model so that it is easier to work with. But like for a real project or like a real paper, you would probably want to do this for a much longer time if you see one of these errors pop up. As a brief disclaimer, when you're doing your group projects, you can also keep things short, just so that it doesn't take like hours to run and instead takes like tens of minutes to run, which I hope is much more reasonable. So if you come across these errors when you're doing your own stuff for the workshop, don't worry about it. If you come across these errors doing your own science, please worry about it and do your models for longer. I'm not affiliated with MC, but I I hope that they approve of my disclaimers. If you're like really curious about like what those errors mean, you could check out the MC documentation, but it's really that you just got to run stuff for a longer time. So once you have run that model and prepared its results, you can again look at the distribution of your free parameters using like a corner plot, for example. So in this particular corner plot, we're again looking at the distribution of our free parameters. The first column is that overall occurrence rate. So it seems to be, again, decently constrained, which is nice. And then these next columns are values for what where the break is the second column. And then the two latter columns are what the slopes could be. The break also generally seems to be well constrained. And you'll note that this is like, because we did it in log space, it is a sort of robust range that is like kind of wide. This is spanning like from negative 0.08 to 0.8, which is like 2-ish orders of magnitude. If you did that not in log space, like in linear space, then this plot would look like way scrunched up because this peak would be like very single valued and tiny. So just an exercise in thinking about when you should fit things in log space. And then again, those two slopes are like decently constrained, good enough for our purposes. So rather than staring at corner plots, let's take a peek at what that model distribution actually looks like. Once more, we can rely on the plot model occurrence 1D function to plot what the best fit occurrence should be compared to the inverse detection efficiency methods predictions. So the IDEM points are shown in those like colored error bars, and then the model is shown again in black and gray. I want to switch things up a little bit, give you time to like internalize this plot, and then tell me what you notice or think about it. So I'm going to give you a couple seconds to ponder, and then feel free to raise your hand and chime in. Kick things off. Does it look good? Shrugs. Yeah, that's the vibe. It's okay, right? It seems decent. Let's talk about the left side, especially at these like close in separations. For as simple as this model is, on the left side, all it has is a line to try and fit this collection of points. So the fact that it runs through most of them is like good enough, probably. And then on the right side, does this feel better or worse than the left side? Worse. Thumbs down. Yeah, it maybe doesn't seem as perfect. Like if you were expecting this to follow a like perfect average of all of these surveys, you might hope that it falls at a little bit of a steeper value, that it's cutting through perhaps the middle of the radial velocity and then into the imaging points. But you'll also notice that the uncertainties really fan out. In fact, they roughly mirror the spread of the uncertainties in the direct imaging data, which could imply that you have kind of little information. Again, there's 6 imaging planets in this entire survey, which are supposed to hold down like an order of magnitude of this distribution. So with those 6 planets, you can get an average, a best guess at where things should be, but there's going to be some intrinsic spread. There is inherently uncertainties that come with having such little information. In a perfect world, you have a lot more direct imaging data. So there's more to work with. It's better constrained, but for now, this is what we're working with. Part of the reason why things look a little bit off, especially on the far sides, is related to the occurrence mass distribution. So this is in the same way that I showed you the flat distribution we fit to occurrence versus radius for Kepler. This is now looking at occurrence versus planet mass. And you'll notice that Kepler is not on this plot because we don't know what the masses of Kepler planets are. So inherently, we should not plot them here. You could try to make use of a mass radius relation to convert the two, but that introduces dependencies on the mass radius relation outside of what we have already introduced. So we'll keep it simple and just try to look at the stuff that is in mass space already. This is, in what I call professional terms, bad, in that it is not clear what you should try to fit this distribution for. There seems to be quite a large spread. There's variability that stems from how little points you have, both from direct imaging, which has like three things. And radial velocity, where a lot of these points are pretty uncertain, they have large uncertainties because there are very few planets at those particular sizes. And even if you were to go through the exercise of changing the number of bins that you were using, say reducing this to 5, you'll also see that a line is not perfectly cutting it. So maybe we can try to use not just a flat line. So in this next exercise, this is the section of the notebook called Modeling Giant Planets with a Size Dependence, which is basically doing exactly the same stuff that we just did, but no longer enforcing the occurrence mass distribution to be exactly flat. So before we get into that, I want to pause, see if there are questions, comments, concerns about the model we just fit or the occurrence distribution of giant planets. Okay, feeling good. This next part is relatively straightforward because we're just adding one caveat to the stuff you've already seen. So we'll start by redefining a new shape function that looks almost identical to the shape function we just used. So again, we have this broken power law component to describe the occurrence semi-major axis distribution. But now at the end, instead of having y raised to the -1, we'll have it raised to another free parameter. We'll fit it with a power law and see if that power law is flat as the best fit distribution. So like, was it a decent assumption that we made? Or if we leave it to its own devices and make it a free parameter, what do we end up with and what does that mean? Once more, the prior function is just slapping some pretty broad ranges on those slopes. So these are roughly the same as what you just saw, but with the added caveat of this new slope for the mass power law. With that defined, you can run through the entire process of importing your surveys, defining your criteria. None of this has changed from what we just worked with. So the only thing that is different is that I have added on the _2D here to say that we are now fitting an occurrence distribution that has components in 2 dimensions, rather than just an occurrence separation distribution, adding on some mass dependence to that. Then you could fit that model or make use of the fact that it has already been fit for you and then prepare those results. Unsurprisingly, once more, you'll get a bunch of warnings from MC. If you add a free parameter to your model, things will necessarily take longer, and you should run your model for longer to make sure that you extra sample that free parameter and the dependencies between free parameters. We kept things the same because we don't have a lot of time. So in practice, please, please, please run your models for longer than what we have done here. But for our purposes, we're just keeping it light. So you could once more look at the distribution of those model parameters. I'm going to cut through this so that we can instead talk about the actual distributions as compared to the inverse detection efficiency method. And you'll now see that things are even worse. You maybe have implicitly assumed that this line does not match these points, but to clarify, there's almost more than a 1 sigma gap. It is certainly not doing a good job at fitting the radial velocity distribution at those farther out separations. And it's like barely hanging on to the imaging distribution. This is perhaps also, a consequence of your binning. So if you change the number of bins to make it a little bit smaller, you will also see this general trend that it's not doing great. And you could even make the number of bins arbitrarily larger. And no matter how you bin your inverse detection efficiency methods, it's a pretty consistent trend that the model is having a bad time. The reason for this is if we scroll down to the occurrence mass distribution and look at the inverse detection efficiency method points have not changed. This is the same stuff that you saw previously because it doesn't depend on the model, but the model is now struggling. This is arguably an even worse fit than when you just assumed that things were flat. It is missing more of these points. And in a world pre-AI, I would have referred to this as the model hallucinating, which maybe doesn't feel good to say anymore. But this is a consequence of trying to simulate planets when you don't have enough information to do that. So our occurrence model is trying its best to account for that there could be, or maybe should be, depending on what your background is, some dependence between the occurrence and planet mass. But there's simply not enough information to figure out what that should really be. And this brings us into a problem of fitting two-dimensional models requires two-dimensional solutions. A large reason that the right side of this model is so off is because there's not a lot of planets at large separations, which, coupled with trying to fit a planet mass distribution where you have 0 far out massive planets or low mass planets, means that you are like your model simply doesn't know what to do. All of the radial velocity points are at these relatively intermediate separations. So there's no RV information, which at these far out separations, which means that when you look at your mass distribution, direct imaging is the only stuff that is far out, but there is no direct imaging data at these lower mass points. So in a two-dimensional perspective, the model simply does not know what to do and has a bad time. So it is visually a worse fit, but sometimes you don't have to rely on just visuals. You could also implement a way of quantifying how good or bad those models are. And to do that, I'll introduce you to Bayesian information criteria. If you've never heard about what the Bayesian information criteria, or BIC, is, it's a metric that weights your maximum likelihood of your model, so like your best fit model and how good of a fit it is, to how many free parameters your model has. So like more complex models are penalized because they are trying to do more with perhaps the same amount of information. So in this case, you could use the get_BIC functions to calculate what the information criteria are for the two models that we just talked about. The giant planet distribution with a flat mass dependence is the top one, and then with a fitted mass dependence is the bottom one. And what I really want to draw your attention to is this line at the bottom that talks about all. This is like the joint likelihood that combines all surveys. You'll note that those numbers are almost the same. And if you haven't rerun these cells, you might actually notice that they are different numbers. This is a random process of sampling a whole bunch of likelihoods. But statistically, a lower BIC is preferred. That means it's a better model, that it's doing more with the same amount of information, but less free parameters. And two BICs that are like relatively close to each other, like within 5 or 10, means that there's not like a statistical edge for one over the other. So I've introduced this quagmire to you, where the information criteria say that these models are like roughly the same, but they are very much so visually worse in the case where you try to fit a power law dependence to the mass distribution when you don't have enough information. And I introduced this just to say that occurrence rate modeling is kind of hard. It is not always obvious what a good model is, and sometimes you have to make judgment calls. Sometimes those judgment calls come from pure vibes of like, I look at this plot and think that it makes me sad. And other times you can rely on statistical arguments because it is within the domain of what your models can constrain. There is not necessarily a perfect solution that works for all situations. So this is an exercise in just trying a couple different things and then relying on the information that you have to make an informed decision of like what works and what doesn't. The one other thing, but let me pause. Are there questions, comments, concerns on that soapbox about model results? Okay. I'd like to introduce you to one other function that also helps with trying to understand the complexities of the stuff that we just talked about. Part of the reason the model looks bad is because there are like, in the case of direct imaging planets, you don't have low mass planets at large separations in your observations, but your model is trying to fit a pretty broad range of masses at a pretty broad range of separations. So one way that you could try to counteract that is to instead evaluate what your model should predict at the range of what each survey can tell you. So for example, in direct imaging, you only have planets that are like larger than 1,000 Earth masses. So why evaluate your model over like down to 10 Earth masses when you could instead just evaluate it from like 1,000 to 4,000 Earth masses? And so this function is called plot occurrence model 1D limited, which also pairs with this function called evaluate model limited. What that limited means as a suffix is strictly limiting your evaluation range to match exactly what each survey has. So for example, Kepler only goes out to 1 AU. So integrating your model only out to 1 AU. That's another example. So if you do that, you'll get a couple different plots, one for each survey that you have. And each of these plots is just showing the model evaluated for that survey's range. So on the left, it's Kepler with the model evaluated only over Kepler's coverage. In the middle, it's radial velocity only evaluated over radial velocity. And you'll see that something has immediately gone wrong, that it maybe doesn't capture the turnover as sharply as radial velocity would suggest. And then in the imaging case, we've gone from overestimating the occurrence in this plot to now underestimating the occurrence, or having a slightly lower value, because the model is trying its best to fit a broad range of masses. So it picks something that works as sort of an average. When you evaluate it over a tiny range of masses, like what imaging can offer you, then you have a relatively low occurrence rate. And when you evaluate it over the full range of masses, you have a relatively high occurrence rate. If that doesn't make sense, don't worry about it. You, in principle, won't run into these problems during your group projects. But again, just a complication of like why modeling is hard. And sometimes we have to be careful about the types of models that we fit and how realistic it is to try and fit them. That's most of what I wanted to talk about today. And that takes us through the full group notebook. So before we talk about like group projects and other things, I want to give you, we'll say, a full calendar minute to just like sit, reflect, come up with any questions, and then we'll run through stuff. And then after that, I'll introduce to you the group projects. So think amongst yourselves. Okay. Questions, comments, concerns about anything that we've talked about in this session today? Great question. So if we go back down to our BICs, like A, what are these errors and like where do they come from? And B, they're pretty big. Okay, so to explain, it's weird to have uncertainties on information criteria. Like in their formal definition, it should be a number. In practice, modeling is never that easy, and you rarely have an exact, perfect, best likelihood function. So what people will instead do is evaluate their information criteria for a range of model outputs, like the range of free parameter options that you get in your like corner plots from your MC posteriors, and evaluating what the BIC should be for that range to then give some estimates on like what is the median BIC, what are the ranges on that BIC, and like how reliable is it. Trying to interpret BICs on their own is numerology. It is a relatively arbitrary process, and they should only ever be compared to each other in cases where all else is held equal. So trying to gauge if the like the number on the uncertainties is too big, like plus 315, or too small, like minus 34, that means nothing. That is entirely dependent on like what your likelihood function is and how it's normalized, which to a certain extent is kind of arbitrary. But in relative terms, it is like they're roughly on the same scale as the BIC itself. Like if you think about logarithmic probabilities, which is where the BIC actually shines, 256 plus 315 is like logarithmically not dissimilar to 256 minus 34. So in a log scale, those uncertainties are like fairly realistic. It's like a decently constrained model, but with a reasonable amount of spread that comes from posteriors. If BICs in general or none of that stuck with you, you can also always just look at the uncertainty envelope, this like gray region on your model, as kind of a vibe check to be like, okay, it's pretty good on the close inside. Like these are nice tight uncertainties. And then it's pretty wide on the far outside. And that's bad because it's not super well constrained. I hope that clarifies things. Other cues.
sensitivity of the survey. Say you find a planet in an area where you are not very sensitive, you have a low completeness to that survey. How do you delineate between a common occurrence planet in an area that's really hard to observe versus a rare but lucky find in that area? Does that question make sense?
Can you just repeat the last part again? It's like
For a local community area, that is intrinsically common versus one that's intrinsically rare, but you just have to get lucky to find.
okay. I think I understand your question. First of all, no one ever asks too many questions. Don't apologize for it. You're fine. But to repeat your question, so like in a regime, when you find a planet in low sensitivity, how do you tell if it is rare or you got lucky or like what is going on? So I'm going to show you some practical examples by going back to our planet samples. A lot of the, like in the top left plot, this is Kepler's transiting giant planet sample. A lot of those planets are farther away, where Kepler has relatively low sensitivity. Conversely, in the places where Kepler has relatively high sensitivity, there aren't that many planets. So on the left, where you have few planets but high sensitivity, what that tells you is that those planets are rare. These are, in the context of this discussion, those are hot Jupiters, which have a frequency of like 1-ish%. We are really good at finding them, but we don't find that many, which means they have to be rare. On the flip side, at far out separations, when you find some planets at low sensitivity, there is admittedly a degeneracy of like, am I finding these planets because they are common, or am I finding these planets because they are actually quite rare and I just got lucky? Like survey completeness is probabilistic. Even if you have like 0.01% completeness, meaning you get 1 out of every 10,000 things, you could just happen to find that one. It doesn't mean that your completeness is higher. This is like what you're getting at is called the low completeness problem. It's a problem that we have with Kepler, especially talking about Earth-like planets, where it's extremely difficult to parse out, are planets rare because we didn't find them, or are they common and we just luck happened? Again, as we were talking about earlier, the solution is to just simulate everything. Like in principle, if you run a billion simulations, you will account for the fact that luck may have happened. So Kepler only happened once, generally, but if you simulate the Kepler process a billion times, you'll have a really good feeling for if the actual Kepler was a fluke or if that's how things really are. So it's a probabilistic problem that you can't solve exactly, but you can try to evaluate it through probability. Other questions? Okie dokie. If at any point, either today or when you're working on your group projects, you do have questions, hit me up. I'm on the conference Slack. I'll be around most of the week. But before we go, I want to introduce to you the group projects and talk about some of the options that you could do if you were particularly captivated by the subject matter. So we have outlined 3 different projects that are all sort of variations on the stuff that we just talked about. All of these are asking what happens to your occurrence rate models or the interpretations they're in when you change different stuff about the modeling process. The first of those group projects is talking about combining surveys in different ways. So at the start, we went through an exercise of just fitting a model with Kepler. And then at the end, we talked about fitting a model with 3 surveys, Kepler, California Legacy Survey, and SHINE. But you could permute those in any ways. You could try to fit a model with just radial velocity data, fitting the intermediate separations. You could try fitting a model with Kepler and direct imaging, but with no radial velocity in the middle and see what happens to the constraints of how well you can evaluate your occurrence rates in the middle. So for that group project and for all of the group projects, if you mosey on over to the workshop page on the hands-on sessions, there is in particular a PDF that talks about the hands-on group projects in more detail. And so in that case, we give you like a little preamble of what I just said. And then sometimes we'll give you like relevant readings if you want to look into things a little bit more, which I'll come back to. But then practically, you could go to the Colab instructions page and scroll a little bit farther down from when we got the notebook that we use today, and you'll note that there are 3 other notebooks that are on each of those different group projects. So if you click on the first group project, which is combining surveys in different ways, you'll find a very similar Colab setup. It has this preamble written by Melanie to like make things run in Colab. But after you go through that, you'll also find there's some like code to help you and like guide you, and then there's some like different sections of code and questions therein to inform like the types of stuff that you might think about if you were doing this particular exercise. So in this case, we suggest here are some different combinations of survey data that you could try, and then some questions that you could ask yourself as you explore those things. So in this particular project, you might imagine fitting a couple different models where you change what surveys you are actually including in the modeling process. And as a little refresher, this is pretty much the only line that I expect would change during this, because this is where you include different surveys. And so you could just remove different stuff depending on the type of things that you're trying to fit. So then the rest of the notebook is cut up into sections with a couple notes, like if you are doing an RV only model, are there concerns that you have to worry about? And then some suggestions for like, how do you actually compare your results? How do you interpret your findings for the things that you are actually doing as a part of this group project? The other 2 group ideas, the second one is depending on the type of model that you fit. Today, we technically fit 3 different models. We did a single power law when we were just looking at Kepler. We did a broken power law, and then we did a broken power law with a extra power law for the occurrence mass dependence. That's a lot of power laws, but you don't just have to use lines. So you could try fitting any number of shapes to the distribution of giant planet occurrence rates. A somewhat common idea is to rely on a log normal distribution, which is a fancy way of saying like a Gaussian or a bell curve, where you just fit like a symmetrical arch, basically, to try and model like where the peak is and what the spread is. So in that second group project notebook, there is a little bit more precursor text explaining what is a log normal distribution and giving an example of a work that has used a log normal distribution to try and model giant planet occurrence rates before. So you could use that as a frame of reference. And then there's also a somewhat detailed section defining like what a log normal distribution is, where can you find the equation for one, because you will have to write like the Python functions to actually fit this model. Log normal distribution is like the easiest alternative to a broken power law, but if you're like really fancy, you could probably try other things. But these instructions are largely formatted around doing that. So again, then there's ideas for like, how do you actually compare your model to other types of models? What are some interpretations or findings that are different between the 2 types of models, that sort of thing. And then the third group project is, I think, perhaps the most involved, but also potentially the most fun, is thinking about how occurrence rates change as a function of stellar mass. So in all of the stuff we talked about today, I was giving you this example of focusing on sun-like stars, and we had that use stellar part of our dictionary for criteria that was just operating over all sun-like stars altogether. But you don't have to put them all in the same box. So the third group project notebook is introducing, like, there's some introductory text on different occurrence rate trends that have changed with stellar properties, especially some examples of things that scale with stellar mass. So if you're particularly interested in maybe figuring out what has been done or setting your expectations for what you might expect to find, then I would encourage you to check out some of those references. But then in this particular group project notebook, we have suggested that you might just split the sample in half. So rather than putting all of the sun-like stars in one bin, what if you put them in 2 bins and then fit 2 different models, one to the lower side of that distribution and one to the higher side? And what happens when you do that? How do the occurrence rates change? Because they will change. And why, if any, do the model parameters change? Like, are there underlying physical reasons why things are different? So there's some introductory text about that and some clarifications on like some changes you might have to make. For example, in the lower mass bin, there are no direct imaging planets, so you only have transits and radial velocity to work with, and some other warnings and precautions to help you with those things. Those are the ideas that we came up with for group projects. But to wrap up this session, I want to say that I am extremely interested in hearing what else you want to do with this. So I mentioned that this code isn't out yet. It's still in development. But as you play around with it, as you work on these group projects, and you also think about how you can connect what you're doing here to your own science, please feel free to hit me up and talk about like what you want to do with it and how we can help you get there. If you don't have the tools already, like what do you need and can we make that happen? And also just like demographics is cool. I'm biased. It's my job. But I think that like every kind of science, no matter what kind of science you're doing, is better in a population context. And so I really encourage you to try this exercise of thinking about how you can connect the stuff that you learn here and in tomorrow's session to your own science and how you can make things a little bit better. I'll wrap up here. Feel free to hit me up with any other questions, comments, concerns. I'll be around for a little bit more. Yeah, thanks for coming. Cheers. Tracy, are they free to go? Everyone is just sitting staring at me. Oh, yeah, I should have. Sorry. A lot of this work was done in collaboration with Gijs Mulders, who I think is online. Gijs, if you want to chime in and say hi through the ether, feel free. He's around. Oh, look, it's Gijs. Hi, Gijs.
Hi. Yes, I have to find my screen. Can you hear me?
Yes, kind of.
Yes. Yeah, I'm following online. So if you've been posting in the Slack, or for the people that are also following the meeting online, they may have been seeing me replying to answers on the Slack channel for the hands-on session. So just like Galen said, like if you have any ideas of what to do or questions about how the code works or conceptually what you can do with it, I'm also available for that. So hit me up on Slack if you have specific questions about any of this as well.
Yeah. So to recap, if you didn't hear in the room, Gijs and I and Ilaria are around both in person and online. So feel free to hit us up on Slack or IRL to talk about code, questions, whatever. But there's 3 of us that you can talk to. Thanks.